In this lecture, we are going to talk about a new concept which is called jointly distributed random variables, which is some we will going to use the another terminology which is random vector. Okay, so what is a random vector? Before going into the definition of the random vector, just recall what was the definition for random variable. The definition of the random variable was that it is a function from sample space to R. Okay, it is a function from sample space to R, and any function from sample space to R we call it is a random variable. Now come to the definition of the random vector. So random vector is a function x from the sample space to Rn, r to the power n. So only change in the definition of the random vector is that instead of r in the random variable, now we have r to the power n in random vector. So random vector is any function from the sample space to r to the power n. Clearly, if I take n equals to 1, a random vector turns out to be a random variable. So in that sense, random variable is basically a special case of the random vector. Now, natural question is that why should we talk about random vector? So to answer this question, again, just recall what was the benefit for random variable. So if you remember what was the benefit for random variable, there are two-folded benefits. One benefit is mathematical benefit, which is basically if I take everything to the real set of real numbers, I can use several mathematical tools which are well known for the real set of real numbers, like summation, integration, countability, uncountability, all those concepts what we have used already. Okay, ordering that x is less than equals to x, those kind of thing I can talk about. Well, now, and another plus point was that in most of the applications, we basically study some numerical characteristics. So, numerical characteristics basically mean that we are in the real life. So, instead of the arbitrary sample space, it is much easier, much better way to talk about the set of real numbers. That means we should talk about some function from sample space to real number. Now, when I talk about the random vector, see that these 2 points is already there because again we have lot of mathematical tools on r to the power n which we can utilize here to study different property of the distribution, different property of the distribution of the probability over the sample space. 1 point, and the second point is that the practical help, which is basically nothing but almost all cases we talk about some numerical characteristics. Well, now if n is greater than 1, we have another extra benefit. What is this extra benefit over the random variable? The extra benefit is can be explained in this way. See that suppose I try to answer some questions like this: is saving increases with income? And if we try to answer this kind of questions, I have to study savings and incomes together. So suppose x is a random variable which denotes income of a household, and z is another random variable which denotes the savings of the household. So most likely it happens that the household who have higher income, they save more. But this is not true always. So the things are probabilistic. That with some probability that higher income means higher saving, with some other probability the higher income maybe implies lower saving. So if I want to answer this question, is saving increases with income, first point is that the technique of the previous chapter will not help us, because in the previous chapter I can study x or z separately. I can study x or I can study z, but I cannot study together. And to answer this particular thing, but this particular question, I need to study both the random variable together. Okay, so that means that to answer this one, I need to study the probability of joint occurrence of the event x less than equals to x and z less than equals to z for different values of small x and small z. Obviously, that instead of x less than equals to x, z less than equals to z, I may have x equals to x, z equals to z, or some combination of these things, greater than x, x greater than x, z greater than x, or something, some combination of all those things. Okay, I need to think about some joint occurrence of some event pertaining to the random variable x and z as well. Okay, but I have to, the main point is that I have to study them together. Okay, and when we try to do this one, I need to think about multiple random variables, because I have two random variables in this case, x and z. So, and you see that this random vector can be fit in this case, because in this case I can think of it is a function from sample space to R. So sample space consists of all the households, and then a function x from s to r to the power 2, I take n equals to 2, then a function x from sample space to r to the power 2 can be defined as first component as income and second component as savings. Okay, clear? So that actually the one of the benefits of the random vector over random variables. And that's why, as we are talking about the joint occurrence of different events pertaining to the random variables, that's why this is sometimes called joint distribution of random variables. Okay, let us proceed. Okay, some more examples that where this kind of scenario happened, that we have to study several random variables together. Actually, there are plenty of examples. If you just think it a little bit, you will find plenty of examples there. For example, I may be interested to know if there is any effect of the air pollution on the blood pressure. I may be interested to know if there is any effect of the attendance of a student in the class and his or her grade. So all this scenario, you see that we have two numerical characteristics that, well, I have in case of the BP and air pollution, I can take the BP of people as well as local air pollution level, and I can try to find out what kind of relationship this could have. Obviously, that intuition says that if air pollution higher, BP should increase, but obviously that we need to study. It's not truth, but we need to study it. But you see that always it will happen that sometime for some people air pollution, if they are in the higher air pollution area, maybe they have lower BP. On the other hand, for some people with the higher air pollution area may have higher BP. So naturally the probability also come into the picture, that because it is not a deterministic thing, that it is not always in working in one direction. So naturally probability will come into the picture. So that's why we are going to talk about the probability and probability of the joint occurrence of several events pertaining to the several random variables. In this case, x and z or x and y, whatever we try to use. Okay. Now, an important point here is that note that x is a function, that random vector bold x is a function from sample space to r to the power n. Now you say that any function from sample space to r to the power n, that can be written in this way, that if I take a particular omega here, that is can be written as x1 omega, x2 omega in this area, xn omega. So first component is x1 omega, x2 omega, second component, xn omega is the nth component. So that means basically each component is a function from the sample space to R. That means each component is basically is a random variable. So that means that if I have a random vector x, then each component of the random vector x is basically a random variable. On the other hand, if I have multiple random variables, if I write them in the vector notation, that become a random vector. Okay, so there is nice interpretation of this one. See, if I have random vector, that means that each component is random variable. If I have multiple random variables, I write in a vector form, it turns out to be a random vector. Okay, clear? Now just again recall that when we talk about random variable, after defining random variable, we talk about the cumulative distribution function or CDF of the random variable. Similarly, in this case also, we will first talk about cumulative distribution function, or which is generally called the joint cumulative distribution function of a random vector. Again, recall what was the definition of the cumulative distribution function of a random variable. The definition of the cumulative distribution function of a random variable at the random variable capital X at the point small x is probability capital X is less than equal to small x. We just generalize this definition for the random vector. How? It is as follows, that in the now we the function, this function capital F at capital Fx from r to the power n to r is the joint PDF of the random vector capital X, where the function at the point x is given by probability that x1 less than equals to x1, x2 less than equals to x2, so on and so forth. Lastly, xn less than equals to xn. Note that these basically mean that it is the intersection of the each individual event. So these events, that comma basically mean that intersection of each individual event. Okay. So in this case, I am talking about joint occurrence of the event that x1 less than equals to x1, x2 less than equals to x2, so on and so forth, and finally xn less than equals to xn. These n events I have, and I am talking about the joint occurrence, the probability of the joint occurrence of these n events, and that is the distribution function at the point x1 to xn. Clear? So this is, now you see that if I have n equals to 1, then the random vector turns out to be a random variable, and in this case the joint cumulative distribution function turns out to be the cumulative distribution function. Okay, so that's why it is basically the direct, I mean kind of a generalization of what we have done in the chapter 2. Okay, so now onward, what I am going to do is that I am not going to write most of the, I mean sometimes I am going to write with general n, but most of the case I will take n equals to 2, and we are going to discuss several results, several examples in this rest of the chapter. But sometimes obviously I will write the result for general n. But notice that most of the cases, the result which I am going to state for n equals to 2 can be generalized for general finite value of n. Okay, and when I write n equals to 2, the two notations I am going to use is that, as before, that bold x means the vector, and then when n equals to 2, the two components will be denoted by either x1 or x2 or x or y. Okay, these two notations I will use. Sometimes the first notation, sometimes the second notation, but as you understand that both of them are basically same. Okay, now this graph actually gives some idea about what is the joint PDF of random vector xy. So suppose this point is small x small y, then in R2 all the points in this region actually have the components less than equals to small x and less than equals to small y respectively. Okay, the first component is less than equals to small x, and the second component is less than equals to small y. Now, when I talk about the distribution function of the random vector x comma y, that is nothing but the probability that the random vector belong to this region. Now you can easily generalize this thing for the 3 dimension. For this dimension, you will have a open cube kind of a thing, and it is the probability that x, y, z belongs to this open cube kind of area. Not cube exactly, that open kind of a cube thing. Okay, so that is basically the physical or graphical interpretation of joint CDF. Okay, now theorem 3.1 is basically a very important theorem, and which says that if I know the joint cumulative distribution function of random vector xy, then I can find out the cumulative distribution function of x as well as the cumulative distribution function of y. Okay, so just again remember that if xy is a random vector, xy is a random vector, x comma y is a random vector, then each component are random variables, so they will have a cumulative distribution function, and that cumulative distribution function can be found from the joint cumulative distribution function, and the formula to find this one is basically nothing but this. What it says? It says that the cumulative distribution function of the random variable x, capital X, at the point small x, can be found by taking the limit of the joint distribution function at the point xy where y goes to infinity. Okay, so the idea is basically nothing but if I try to find out the cumulative distribution function of x, I have to take the limit with respect to y. Similarly, if I try to find out the cumulative distribution function of y, I need to find out the limit with respect to x. And keep in mind, when I try to find out the cumulative distribution function of x at the point small x, here this x is fixed and this y has to take to infinity. Similarly, in this case, when I try to find out the cumulative distribution function at the point y, then this y is fixed here, and I need to take this x goes to infinity. Okay, let us first see the intuitive idea. What is the intuitive idea behind this? Before going into this, again recall what is the cumulative distribution function of a random variable. So cumulative distribution function of a random variable x is nothing but that x is in this region, right? X is in this region, that x is less than equals to x. The probability of this one is basically our cumulative distribution function. The probability of this part is the cumulative distribution function. Now, in case of the two random variables, as we have already pointed out, that joint cumulative distribution function is the probability that the random variable is in this region, okay, in this shaded region. Now, if I try to find out what is the probability that x is less than equals to x, that means x is in this side. That basically means that obviously x is in this side, but y can take any value from minus infinity to plus infinity. And intuitively, if you take this y, the point y goes to infinity, that basically means that for y everything is covered and I am only left with that x is less than equals to small x. And that's why that this thing is going to be true. And that was basically the intuitive idea why this thing is true. I hope that intuitive idea is fine with everyone. That if I take y goes to infinity, then basically this point actually goes to this goes in direction and goes to infinity, because my x is fixed, so it basically travels in this way and goes to infinity, and then basically I will cover all the points where x can take all the values but x is less than equals to y. And that's what we try to find out. That's probability we try to find out, because that is the probability that the probability of that event is basically the cumulative distribution function of the random variable x. Okay, hope that intuitive idea is fine with everyone. The mathematical proof, again almost same as that, the same technique we have used before. We have to consider an increasing sequence of events, and then we need to take a n, which is basically x is less than equals to x and y is less than equals to yn. Then it is easy to see that an is an increasing sequence of events. So the limit of an will be the union, and union of an you will be able to show that this is nothing but this set. Now I take the limit on both sides and the proof is complete. Check the proof. It is basically as just technique is similar to that we have used to show the properties of cumulative distribution function. And check the proof. If you have any doubt, you ask me in the doubt clarification. Okay, so this theorem, you see that we have basically wrote down it for two random variables, for a random vector having two components. But this theorem can be easily generalized for more than two random variables, a random vector having more than two components. So let us just see that in the remark, suppose I have now three random variables x, y, z, and the random vector x is having the components x, y, z. And in this case, suppose I try to find out what is the cumulative distribution function of x. Then what I have to do? I have to take the limit with respect to the raised to, that is y and z. Again, the idea is same, that if I take x and z goes to infinity, that basically means the whole range from y and whole range from z are covered, and I am only left with x is less than equals to small x. Capital X is less than equals to small x. Okay. Similarly, if I try to find out the cumulative distribution function of y, I need to take the limit with respect to x and with respect to z. Obviously, order does not matter. You can change the order of the limit. Same thing happens for the z. Now, not only that x, y, z individually, even if I try to find out the joint cumulative distribution function of x and y, I can do that. I can find out the joint cumulative distribution function of x and y from the joint cumulative distribution function of x, y, z. And the idea is again same, that I have to find out for x and y, so I have to take the z goes to infinity. Similarly, if I try to find out x and z, I have to take y goes to infinity. So, if I have to find out the joint cumulative distribution function of a subset, then for the rest of the random variables, I have to take the corresponding component goes to infinity. Okay, hope that this is okay with everyone. You will be able to find out the cumulative distribution function of random variable given the joint cumulative distribution function of a random vector. Okay, now note that. Okay, now the next thing was what we need to, well, one terminology that we generally use in this case is that when I talk about the random vector, we generally write it the joint cumulative distribution function, JCDF. When I talk about a subset of the random vector, we need to talk about that it is basically nothing but for example, in the previous case, in this case, this is basically the joint cumulative distribution function. And in this context, generally, this distribution function, instead of saying it is the CDF of x, we normally say it is the marginal CDF of x. Similarly, in this context, this is the cumulative distribution function. But when we talk about the marginal, instead of saying it is the joint cumulative distribution function of x and y, we generally say this is the marginal cumulative distribution function of x and y. So whenever we have a subset, we call it is a marginal one. When we have the full one, we call it is a joint one. Okay, this is a terminology. I mean, both the terminologies are used, that it is the joint CDF of x and y, as well as this is the marginal CDF of x and y when the original one is this set.